So yeah, welcome everyone to I believe I think the sixth talk or the fifth talk of the Equivariant Ell Cohomology seminar. So today we have Timon Thanassis from University of Regensburg, and he'll tell us about the construction of global cohomology theories. So Timon, please take it away.
All right, thanks, Amartya. So today we're going to talk about constructing global cohomology theories. And so basically we'll give a crucial construction that we will need for the next talks in the seminar. Um, so we will start with what we'll call a pre-oriented abelian group object in some infinity category X. And out of this, we'll construct a global cohomology theory, which should sort of be a suitable cohomology theory that has equivariance properties with respect to all suitable groups, compact Lie groups, simultaneously. And this should also be colimit preserving. Therefore, we will actually take this orbispace category as the origin category. So let's maybe give a brief outline of what the aim of this talk will be. So the first question we'll tackle is what do we actually mean by abelian group object in an infinity category? What we mean by pre-oriented, and how do we construct the cohomology theory out of that? So for the construction of the cohomology theory, we'll actually use a stacky version of Pontryagin duality. So recall that for Pontryagin duality, you sort of get a dual to a group by taking maps from this group, the Hom groups from this group into the circle group. And this should be an involution. When you apply Pontryagin, when you take the Pontryagin dual twice, this should actually be isomorphic to the group you started with. So we will need a stacky version of that. So before we start, let's maybe review some things from last time. So a notion that we'll need is the notion of a topological stack, which will be a functor. It's a notion of a stack in the context of topological spaces. So it should be a functor from topological spaces, a contravariant functor, into groupoids. And this should satisfy some sheaf condition, which is basically for a covering as given below by this P. This should actually give an equivalence between this limit, sort of the intersections and the whole space that we started with. So it should satisfy this descent condition. And so top prime here isn't, don't worry about that. This is just set theoretic details where you want some countable CW complexes to be in there and so on. But we'll neglect that for the moment. So this actually gives us a 2-1 category of topological stacks, but we don't want to work with this 2-1 category of topological stacks. We actually want to work with some quotient, some infinity categorical quotient by a standard action of the cosimplicial simplex. And so, yeah, this should have sort of the elements of stacks, but it should the mapping spaces there should sort of interpolate homotopy. So we'll start with the global orbit category, which should be the full subcategory of this stack infinity, which consists of objects of the form BG for compact Lie groups G. And we'll construct orbispaces as functors from the global orbit category to anima, and we'll denote that by S orb. I guess for the sake of keeping notation, for keeping the notation for the next times, I'll actually write S instead of an. So I'll keep it only in a few cases. Otherwise, I'm sorry, I will have replaced S by an for convenience.
Sorry, could you repeat what an is?
Yeah, it's basically just S, basically just spaces. Infinity group.
Oh, okay.
Yeah, it's animal.
Thanks.
So
Sorry, shouldn't there be an op on orb? Should an orbispace be
yeah,
pre-sheaf
sorry.
on orb?
Yeah.
Okay.
A contravariant functor. So to every topological stack, we can associate an orbispace, which is sort of represented by the topological stack that we had. And so therefore we'll use functors out of orbispaces to be an adequate origin category for a cohomology theory on topological stacks. So yeah, I mean, we passed from the global orbit category to these orbispaces because we basically want to have colimits. All right, so how does this align with what we're going to do subsequently in the seminar? So we want to apply this construction to elliptic cohomology to create some sort of an equivariant elliptic cohomology theory. So we start with some non-connective spectral Döding-Mumford stack, and we take some oriented elliptic curve over M. And so today's construction will actually allow us to get some functor L from orbispaces into sheaves on our Döding-Mumford stack. And therefore we will actually construct some also variants with quasi-coherent sheaves instead of sheaves, and get functors which should be sort of our equivariant elliptic cohomology theories, which will stand G spaces to quasi-coherent sheaves on this stack that we've constructed. And so next time, the talk that Amartya is going to give is gonna study how this construction that we'll give can actually be used in the classical equivariant K theory. Then the talk after that is going to construct these elliptic cohomology functors. And the last talk is going to be specifically on equivariant elliptic cohomology for G equals to T, the circle group. So now we want to go towards the construction that for our cohomology theory. So we should maybe first see what kind of abelian group objects we want to work with. So we're going to use a strict notion of abelian group objects, which is basically going to use Lauvier's algebraic theories. So Lauvier's theories take an infinity category with finite products, a unit object, and a functor from the nerve of finite sets, taking the opposite of that, into the theory, the Lauvier theory, which should send the singleton to the unit element, and this map should be essentially surjective. So basically, we get sort of a skeleton of what the algebraic theory should do, and taking functors from this prototype into a category, we can actually get our algebraic theories on this specific infinity category. So here we start with the Lauvier theory of abelian groups. So this should be sort of the prototype of what abelian groups should look like algebraically. And so we take the opposite of this Lauvier theory to be the full subcategory of abelian objects in set, which consist of finitely generated abelian groups. And so we can give a skeleton of this of T-ab by a category that consists of objects n, so of natural numbers, and the mapping spaces should be given as follows. So then we can define an abelian group object in an infinity category X to be given by finite product preserving functors into X from the opposite of our Lauvier theory. All right, let's maybe look at some examples. So when X here is the ordinary category of sets, then the abelian group objects in X actually recover ordinary abelian groups. So as we mentioned, we're gonna look at sheaves on the big Ital side for some Döring-Mumford stack. So actually, we're gonna work with also abelian group objects for infinity topoi. So specifically, let's look at what happens for anima or for infinity groupoids. Then the infinity category of abelian group objects in anima is actually equivalent to connective chain complexes. Also, topological abelian groups give examples of abelian group objects in anima. So let's start with maybe a convention that we'll need. So we'll denote by orb ab this full subcategory of objects of the form BG for abelian compact Lie groups. So this will be important because the main outline of what we want to do is that first we want to define a cohomology theory on orb ab, so on these abelian compact Lie groups explicitly. Then we want to extend it to the global orbit category, and then so we want to left-hand extend it there, and then we want to extend it to orbispaces. So this will be the base for our construction, the BG for abelian compact Lie groups. So that was basically what we needed for abelian group objects. So what do we mean by pre-orientation? So we start with an infinity category which admits finite products. So a pre-oriented abelian group object should be a specific kind of abelian group object. Let's call it A inside of our infinity category X. That should be equipped with a morphism of abelian group objects from BT for the circle group T to map X points into A. So we should have this sort of pre-orientation on there. We can construct the entire infinity category of pre-oriented abelian group objects in X by taking the pullback ab X. So this pullback that you see, where the map that we have from abelian group objects in X to abelian group objects in anima is co-represented by the point. So we can actually give an equivalent characterization of what a pre-oriented abelian group should be. So we can construct this Lavier theory of pre-ab, so pre-oriented abelian groups, to be the full subcategory of pre-oriented abelian group objects, of abelian group objects, there's a mistake there, which is equivalent to BT to Z to the N cross BT. So this should capture the pre-orientation. And the full subcategory of pre-oriented abelian group objects. I'm sorry, this was correct. So we take a full subcategory of these pre-oriented abelian group objects in anima, and we can actually model what the entire thing will be from these. So for an infinity category with finite products, we can actually give an equivalence from the category of pre-oriented abelian group objects in X to finite product preserving functors from this Lavier theory into X. So now we'll come to the stacky version of Pontryagin duality that we wanted to have. So we need to define what this duality should do. So we actually take the mapping space in the global orbit category, and this should be represented. We want it to be represented by BT. So this goes from the subcategory of the global orbit category, which only contains compact abelian Lie groups, and this goes to pre-oriented abelian group objects in anima. And so what do? We start with X and send this to send this to a pre-abelian pre-oriented abelian group objects, which go from this BT, or the mapping space from the point to BT, into the mapping space from X to BT. So as a concrete example, we can see that if we apply this Stacky-Pontryagin duality to BG, then it actually gives us G hat in the traditional sense with cross BT. So maybe to give we will not need that, but just to sort of motivate the terminology, the shifted Pontryagin duality functor that we have is actually fully faithful. And all right, so we want to give a construction where we start with a pre-oriented abelian group, and we get a functor from pre-oriented abelian group objects in anima to X. So when we precompose that with the shifted Pontryagin duality functor, we actually get a map from these abelian global orbit category into X. And so this we will extend afterwards to get us the final functor that we really want to have. So we'll maybe need a few technicalities now. So when we start off with a Lavier theory, and we take a complete infinity category with finite products, defining Tx to be the finite product preserving functors from T into X, then we actually have that the functor that is indicated down here in the proposition is actually an equivalence. And so this is the crucial ingredient, technical ingredient that we'll require in our construction. So we can actually give we should actually maybe discuss what this internal mapping space should be. So this should basically be represented by should sort of represent the functor that is given down here, which sends X into the mapping space that I've written. So we will not give an entire proof of this because the technical details are a bit cumbersome, but let's maybe sketch how the proof will go. So concretely, we will actually give the inverse of the functor that we wanted, and we can actually give the inverse by the restriction. And I mean, we can prove that this is an equivalence. This is actually done in higher topos theory, but we won't necessarily have the time to go through the full argument. So basically, it uses that that when you take finite product preserving presheaves on a category that are finite product preserving, this is the smallest full subcategory, closed under filtered co-limits, geometric realizations, and contains the essential image of the Yoneda embedding. And then this is basically used to then prove that you get a trivial fibration. But let's maybe take this for granted, that this restriction actually gives us an equivalence. And now we actually want to identify the inverse of this more explicitly. So what do? We start with an object A in T of anima, and an object B, this is incorrect here, this should be T of X, I think. And so the functor that sends X to the mapping space in T of anima from B to the mapping space in X from X to A, this is actually representable. So this is not so clear, but what is done in the Gepner-Meyer paper is that they look at those those x that actually satisfy that, and they show that this is complete, and so then they extend that by seeing that this works for a certain subclass, for finitely generated for a specific subclass that they can then extend to all of x. And so since this is representable, one can actually, when one takes the functor that goes from t anima up plus tx to p of x, where here the arguments are just a and b, that this functors through the internal mapping space. And there you can actually give a concrete description of what this looks like. So thereby you can actually prove the above equivalence, since we have seen what the inverse will look like, the inverse of the inverse, basically. All right, let's maybe leave the proof aside for a minute. We'll not need it. So we'll choose a subcategory, TA finite, T of anima finite, which should be the smallest subcategory containing the finite T algebra on one object closed under finite colimits. Then we can actually refine the above equivalence to an equivalence from T of x to fun R from T of anima finite and the opposite category into x. So in order to prove that, basically you just need to show that the right-hand side corresponds with the right-hand side in the proposition. And specifically, when we take a specific Lavier theory, let's say the Lavier T pre-ab that we define for pre-oriented abelian group objects, then we get an equivalence as we see it here, which goes from pre-oriented abelian group objects into these left exact functors from pre-oriented abelian group objects from anima, when we take this finite subcategory. So the subcategory that we defined above, and we map that into x.
Do you want a question real quick?
Yes.
So the equivalence that you have, like dx maps to, so shouldn't that be left exact functors?
Where is it? What do you mean exactly?
The first equivalence that you have.
So the one with the proposition.
Yeah. No, I mean, so this where A maps to like B, that maps to.
Oh, okay,
like
okay. But I think that this should be fine. Let me just.
Oh, can you just look it up, maybe?
Yeah, you're right. You're right. Yeah, you're right. Sorry.
Oh.
So yeah, thanks. So this should be left exact as well. So let's maybe start with the construction now. So we start with a finitely complete infinity category. And so then we actually have that the shifted Pontryagin duality functor will actually factor through this subcategory that we just defined. And so we can basically see that by concretely seeing what happens to groups when one applies, so to classifying spaces of groups when one applies Pontryagin duality. So when we take our functor phi, remember that this is just the phi here below. So when we compose that and precompose with Pontryagin duality afterwards, then we can actually get a functor from pre-oriented abelian group objects in X to functors from this abelian global orbit category into X. And so we can actually give a concrete description of what happens when one applies the upper functor that we give by the composition. So for a co-complete infinity category X, and for every element A, and for every pre-oriented abelian group object A in X, we can left-Kahn extend this functor that we just obtained from the abelian global orbit category to the entire global orbit category. And so then we get a functor actually from the global orbit category into X. And when we pass to the universal co-completion of the global orbit category, which is just orbispaces, then we actually get the functor that we wanted to have. So more precisely, we have obtained a functor which goes from pre-oriented abelian group objects in X to colimit preserving functors from the category of orbispaces into X. And so we'll need a final proposition for the subsequent chapters, whereby when we start with an infinity category X with finite limits and a pre-oriented abelian group object in X, then the functor that we have just constructed can actually be concretely determined as I've written it down. Of course, it shouldn't be functor underlined, it should be map underlined, so it should be the internal mapping space. And so when we take the fiber of a map from one of these powers of the circle class of the circle group to another power of the circle group, then we can actually concretely determine the right-hand side as being given by the fiber of applying our pre-oriented abelian group object X to Z mod n going into Z mod m. So let's maybe shortly discuss the proof of how this works. So we start with a forgetful functor from pre-oriented abelian group objects in X to abelian group objects, and so this has a left adjoint, which we can actually concretely give by sending some abelian group object H to H cross BT. And so the pre-orientation on this will be given by the inclusion on the second factor. So since we have we have a concrete description of what the Pontryagin dual will be on these BG, we can actually see that this lies in the image of the left adjoint. And so actually we can give the description of this functor f that we constructed more explicitly by these internal mapping spaces. And given the fact that Pontryagin duality then sends limits to colimits, actually f will preserve limits, and this gives us the last claim that we had. All right, so as a small recap, what we have done is that we started with these pre-oriented abelian group objects, and we managed to construct a global cohomology theory out of that. And so in the subsequent talks, we will require that, as we said, for elliptic cohomology to construct basically our version of equivariant elliptic cohomology. That was a bit faster than I would have thought that it would need, but I think that we don't have anything else to discuss.
So let's thank our speaker. And now we are open to questions, I guess.
Yeah, maybe we can postpone the questions to become post-recording questions.
Sure, that's totally fine with me. So